Okay, this is kind of going back and forth between recursives and explicits now, given one state the other. So let's see how you did. Now, if they gave me the recursive, they're wanting the explicit here. And so I'm starting it with f of n equals, noticing here that that's what we're calling this function. And we want to state where my function begins, what it's adding each time into the previous term. So let's go grab the stuff from up here. Notice it says we're beginning at 18. We're then adding 7 each time to the previous term starting at time 1. And so I'm going to go highlight where these all came from so you can apply this rule across the board. But so here comes where the 18 starting was. The adding 7 common difference came from right here. And then the time 1 comes from right there. So go apply that across the board here. Pause this video, try the next one. Okay, let's see how you did. So it begins with 15, subtracting 9 repeatedly to the n minus times 0. Now, remember, in class, people ask, do I have to put the 0 on that one? No, you can just do minus 9n or minus 9 quantity n minus 0. Both are acceptable. All right, pause the video, try the next one, see how you did. All right, here we go. F of n equals, begins at negative 9, adding 12. All right, so begins with negative 9, adding 12 repeatedly to the one before time 1. So again, just to reiterate, where is this coming from? This right here is coming from negative 9. This right here is what we're adding each time. Your common difference goes here, and then the time 1 comes from right here. Okay, hopefully you found all those easily. All right, looking at this next one, we've got f of 1 equals 20, f of n equals f of n minus 1 minus 2. So we'd go f of n equals, begins with 20, subtracting 2 each time to the one before time 1. So where does this 1 come from? Because this is f of 1 equals. Notice they're all f of 1 equals. We will talk later this week about what happens if that's not a 1. So here I go with the next one. Begins with negative 4, subtracting 11 repeatedly to the previous term. And finally, begins with 2.5, adding 3 repeatedly to the previous term. Okay, see if you can make sense of that and why all those numbers appeared in that order. Now we're given the explicit, and your job is to write the recursive, so going backwards from what we just did. So here I go. F of 1 equals 15. So wait a second, where does that come from? Right here is telling me this is an input of 1 or a time 1 function. And right here it's telling me that the first output is 15. So notice where that shows up here in the recursive. Then we always start with the same thing for the second part. F of n equals f of n minus 1. F of n equals f of n minus 1. And then the pattern goes there, plusing 7 in this case. So where's that come from? That guy right there. How'd you do? So pause the video, try the next two, and then let's check them. Okay, let's go see. Did you get f of 0 equaled 8? Wait, what? Let's go check where that came from in just a second. And then f of n equals f of n minus 1. Did you get minusing 2? So why is this a time 0 function? Because technically right here, there's no number at the back or no parentheses with an n minus 1. So that's what tells me it's the time 0 or beginning step of the function. And you can write this in or not. It's up to you. Okay, last but not least, how'd you do on this one? F of 1 equals negative 2. F of n equals f of n minus 1, plusing 5 every time. Notice that when this says n minus 1 in the function, it's a positive 1 right here. Notice that this negative 2 began the function is right there. And notice that the plus 5, the pattern shows up right here. Notice that this section is always the exact same in our recursive notation. F of n equals f of n minus 1. F of n equals f of n minus 1. Okay, So looking at this next one, I actually like to start with number 13 and work backwards. You'll see why in a second. And yes, there's a formula that goes with this. There's actually two formulas that you may remember. But so looking just like ignore this and ignore this at just this section right here. If you grab a calculator and you find out that big jump difference, if I grab my calculator and do 85 minus 52, I'm seeing that that's 33. But that's doing it in one big jump when in fact it's supposed to be split into two small jumps, right? And so if I split that into two small jumps, I'm going to get 33 over 2, which is 16.5. By the way, all of these are arithmetic, meaning adding or subtracting, so keep that in mind. So from a 52 up 16.5, so 52 plus 16.5, I'm getting 68.5 right here. And then if I take 68.5 plus 16.5, I get the 85 that's already there. So check, that sounds right. And then I do it one more time because they asked me to go past that one. So 85 plus 16.5, I'm getting 101.5. And then how would I go backwards to get this one? You got it. Let's subtract 52 minus 16.5. How'd you do? So one of the formulas that we used on this is called slope formula. y2 minus y1 over x2 minus x1. And that's this little format of what I did right here. So the two jumps technically came from these numbers over here. Oops. Shoot, I wrote the wrong one, sorry. 4 minus 2. Okay, these right here. So I subtracted these and I subtracted these over each other. That's the slope formula way. That means that I got a slope of 16.5. The other way that a teacher might have taught you in their class was that we started at 52. We were adding some unknown number, common difference D, repeatedly, and then these two numbers here come into play, the 4 and the 2. And that when I do that, I should end up at 85. So if I start here at 52, and then I add repeatedly some unknown number, 4 minus 2 times, that comes from over here, it should equal 85. And then we solve this formula, and we end up doing the same exact steps. We end up doing 85 minus 52 divided by 2. And we get a common difference of 16.5. So whichever formula you learned with your teacher last year, or whichever formula makes more sense for you, slope formula or the explicit point slope, either way, you can use a formula always that works. So now let's go. When there's more jumps than 2 jumps, when there's more spaces in between the numbers, let's see if we can apply it. So in this case, this is got an output of 100. I'm going to be adding some, actually subtracting some common difference here, 3 jumps, 1, 2, 3 times. But just in case I don't know where that comes from, I look over here, 5 minus 2 times. And if I add that number repeatedly, 5 minus 2 times, I should end up at 73. So I begin with 100. I do this common difference, unknown, 5 minus 2 times, and I should land at 73. So it's the table that's building this equation for me that I can solve and get my common difference. So here I go solving it. 5 minus 2 is 3. 73 minus 100. Grabbing my calculator. Notice this is going to give me a negative number, which is what I want. Oh, it's Miss Sanchez's favorite number, 27. And I should get a common difference of negative 27 divided by 3 is -9. That means I'm subtracting 9 at every step. So 100 minus 9, that gives me 91. 91 minus 9, 82. 82 minus 9, yep, I got 73. What if I want to go backwards? You got it. 109. 109 minus 9 would give me 100. Now, what if you didn't want to use this formula way? What if you wanted to do the other formula way? You probably did 73 minus 100 over 5 minus 2. You still should have gotten negative 27 over 3. You still should have gotten negative 9. It doesn't matter which formula you use, both work. Common difference, slope, same. Okay, last but not least, pause this video, try this one on your own, see how you do. Here's a table that starts at 12, is adding some common difference D, 4 jumps, or 5 minus 1 times. And after that, we should land at 40. We solve. (40 minus 12), grabbing my calculator, is 28 divided by 4. And we get D equals 7. That's my common difference. So 12 plus 7 is 19. 19 plus 7 is 26. 26 plus 7 is 33. 33 plus 7 is 40. Now, what if you wanted to do the slope formula way instead? You could have done 40 minus 12 over 5 minus 1, 28 over 4. Hey, it's still 7. Yay for me. Okay, how'd you do on those? We'll be practicing them tomorrow. Last but not least on this page, it's you noticing the pattern. Notice these are still all arithmetic, so we're still just adding or subtracting. So 28 minus 11, I get 17. So continue that pattern, 62 plus 17, 79. 79 plus 17, 96. We're going to write the recursive and explicit. Remember, all sequences are assumed time 1. So f of 1 equals 11. F of n equals f of n minus 1 plus 17. Explicit, f of n. Sorry, I'm not liking how I squished this, guys. Hang on a second. F of n begins with 11, adding 17 each time to the previous term. Where does the n minus 1 come from? It's an assumed time 1 function if it's not brought up otherwise. All right, what's the 7th term? We're now going to use the explicit to plug in. So we go f of 7 equals 11 plus 17 to the 7 minus 1. So what just happened? Right here where there was an n, we just plugged in 7, and now we're going to solve. Grab your calculators. We do parentheses first, and then 17 times 6 is 102. And then 102 plus 11 is 113. Did you remember how to plug in that 7? All right, the next one we notice is going down by 9. It's subtracting 9. These are arithmetic, so it's not dividing. Be careful. So 0 minus 9 again is going to be negative 18. The recursive goes f of 1 equals 27. F of n equals f of n minus 1 minusing 9. F of n equals begins with 27, subtracting 9 each time to the previous term. Assume time 1 for sequences. 15th term means I'm plugging in 15 to this explicit. All right, so we're going to write f of 15 equals, and we're going to do parentheses first. Again, where did this come from? Right here where there was an n, right here where there was an n in the explicit, we're now plugging in 15 to solve. So we go 14 times 9 is 126. 27 minus 126 is 99. Do you have to write this notation all the way down? You do have to write it in the last step, and you have to have the equals the whole way down. So 15 minus 1 was 14. 9 times 14 was 126. And then 27 minus 126 was negative 99. How'd you do? Great job on this page.